Okay, let's see if this works. Right. Yeah, so let me double check again. I hope you guys can hear me. Sorry about that. Is this fine? Okay, I guess we'll give it a minute to see, let folks join in again. Okay. Check, double check. Okay, that looks fine. Okay, check. Can you hear me now? This should work, technically. Okay. All right. Yeah. Okay, great. Now audio is working fine. So sorry about that. Not too sure what the problem was. I had to just pull the plug out and put it back in. So it now works. Okay, so quickly to sort of recap what I was talking about. So yesterday, or rather in the last stream, we was talking about JTAG debugging. And, because we came across a problem and we were wondering, how do you fix this? So we took some time and delved into what JTAG is and, how we can go about debugging it. Sorry, how we can go about using it to debug your code. So the board that we were using was the i.MX 8, the i.MX 8-M Nano. So it has a JTAG port over here. Using this JTAG port, you will be able to debug code that is running on the processor. All right. These pins are your general purpose pins, input output pins, but this is your processor, and that this is sort of connected to your JTAG. And we figured out that you pretty much JTAG is this 4+1 optional wire connection, where you need 4 signals plus 1 optional signal to sort of debug any code that is running on the processor. That means debug in the sense, if you'd like to halt execution, if you would like to apply a breakpoint, if you would like to skip over an instruction, if you'd like to change memory or inspect registers, etc. That's what we mean by hardware-based debugging, and JTAG is one of them. And we looked at that in the last talk. So today what we're going to be doing is just an extension of that, and that this is also hopefully going to be a short stream where we will now try and see how to run Rust, basically start up Rust code on the actual processor. The last time we were mostly looking at the debugging portion of it. We didn't get to actually bring up the board and have Rust code run on it. Now we'll try and do that. All right, so that's sort of the goal, basically to get Rust running on the ARMv8-A processors, which is basically the ARMv8 application processor, not the microcontroller processors, which we've already done quite a bit. This one's the application processor. So we'll look at the basic pieces, and then we'll dive a little into the architectural aspects of ARMv8-A. It's not a whole lot different, but it is different. But you'll feel familiar because we've been working with Cortex-M for a while now. All right. Okay. So let me quickly go ahead and sort of just jump into what the agenda is. So I've begun putting the agendas and all together. So just so that, it's clearer what we're doing, etc. So we'll first focus on how do we, sort of bring up basic, how do we actually jump from what's called assembly code into Rust code. So whenever you're trying to bring a board up, it's usually going to happen in assembly. So the first few instructions you will write by hand will be assembly instructions. And we look at why that is. So you'll write a couple of instructions using assembly, not using a traditional, high-level programming language like C or in this case Rust. You will use assembly because you need to do a certain set of things that, depending on how the compiler compiles your code, can become very tricky. So in order to avoid that, you basically write the instructions by hand. So that's the startup code. Then what you need is you need a way to tell your compiler to say, okay, this is my code. I would like you to lay it out in memory in this order. That means the instructions or the text section goes first, the data section goes next, the other sections like the global offset table or whatever they are. I want to be precise in the way the program is, the content of my program is actually laid out in memory during execution. All right. So that's what you need a linker script for. Essentially what it does is all the compiled artifacts, the objects that are built, you need to sort of stitch them together and create one nice little executable, and the linker script is going to help with that. So we need that. And then finally, we need, the actual Rust code that you get to run, right? Whatever Rust code that you have written, that's the whole point of this talk, because we're porting basically Rust boot. The idea is to port Rust boot, but before we get to all that, we need to do the basics. So that's the first 3 steps that we need to do, and I'm sort of going to walk through that right now. Sorry. So let me pull up the IDE. Okay, first things first. Is the IDE, the font size okay? Or should I make it bigger, smaller? Right? Okay, let me just check. Slightly increase. Okay, let's do that. How's that? Good. We'll just sort of make it a little smaller. Is that better? A little more? Okay. All right, so this is good, is what I'm hearing. So I'll just sort of continue. Okay, so let me actually pull up. So this is our Rust boot project. We've, just for, because ultimately we're going to be porting Rust boot to this particular board. So I've started adding the pieces that I need. So I'm just going to walk you through the pieces that I've added for this specific, for this specific implementation. So there are only 2 things that we've added. We've got in boards, we'll be adding a bootloader. That's the actual bootloader that's going to be compiled and programmed into the board. That's one, which is what we're calling the i.MX So we'll dive into this. Yeah. And then we have the hardware abstraction layer. In the hardware abstraction layer, we have a folder for the specific board that we're working on, which is again here. Right? So this particular hardware abstraction, I'll just sort of walk you through what's happening over there. But before I actually do that, let's kind of jump into the first piece, which is the startup code. What is it really about? Okay. So if you go into bootloaders and you look at the source, you'll find the file called entry.s. Right? Now, when, so like pretty much every board out there, it's not your code technically that gets to run immediately on power up. There's a bunch of things that happen. There's some, basic input output tests that happen. All of that is very, hardware specific, etc. But finally, the vendor's ROM code, that means read-only code that's present in read-only memory, that's immutable, that gets to run first. All right. Once it does its job, it looks, depending on the vendor's implementation and whatever standard they've got going, because none of this is standardized. None of these boot methods are actually standardized. Like, for example, in the x86 world, you have something like a UEFI, which is basically a boot standard. That is not present in the ARM world, because the ARM world deals with devices of very different, sizes and shapes and power budgets and performance profiles, etc. So it's been very difficult to sort of standardize. So that's primarily the case. But in any case, think of it this way. You'll have some ROM code. The ROM code does its thing, whatever it needs to do. And then it needs to hand over control to the next piece of code or firmware that's going to execute. It's usually a second stage bootloader. It's usually, not all the way, not always. Right? So the job of a bootloader is nothing but to create an environment that's good enough to load whatever comes after it. It could be an operating system, or it could be some other intermediate firmware, whatever that is, right? So at that point, once the ROM code is done, it hands over control to, in this case, let's assume that is going to be Rust boot. It hands over control to that. And then when your Rust boot code is actually supposed to be perfectly executing, this is where it lands. The very first instruction of your program or of Rust boot, the bootloader, is in this file. And specifically, it's this particular section, which is, the starting point. That's why I've named it start and also put another global variable over there. I'm calling it reset. All right. Does that make sense? Yeah. Should be sort of mentally make sense. You can compare and contrast this with your Cortex-M world, where in the Cortex-M world you have like two pointers that are present at the very start of the memory memory map, which is 0, 0, and 0, and the first 4 bytes and the second 4 bytes. The first one is the reset vector, and the second one is the stack pointer. So that's the conventional booting mechanism for a Cortex-M processor. But in the Cortex-A world, you're going to be doing this. You're basically going to be writing some assembly code that will make up the first part of your whatever code you want to execute, right? Okay, so now that we're here, so I'm not going to directly jump into the assembly, because if you actually read the comments, which I will be I'll be pushing this out pretty soon. If you read the comments, it's pretty straightforward what I'm going to be doing. I'm going to check what is called the current execution level. So what you see over here, which is current EL, SCR EL3, all of this is stuff. These are registers that are already part of the basically a part of your machine. The compiler knows of this, so you don't have to do something extraordinary to sort of include them. The compiler knows what current EL is. It's a register. The compiler knows what SCR EL3 is. It's another register. This is a system register, as you can see over here. These are all system registers that we're using, basically. System registers are registers specific to the system. All of them are not accessible from different places. The key thing that you need to keep in mind when you actually look at this is this EL3, and then there's this EL2, and then there's this EL1. These are called exception levels. Exception levels are nothing but, these are privilege levels. You can sort of think of them like that, but ARM calls them exception levels. We'll also see why they're called exception levels. But exception levels are like privilege levels. So you can be operating at one level, if the lowest level is 0, actually I don't know if that's the lowest level, but according, at least what I know is that 0 is the lowest level, which is EL0. Then you have EL1, then you have EL2, and EL3 is like the highest privilege level that you can have, where your code is probably running. In our case, technically, Rust boot or any bootloader at this stage is actually running at EL3. Okay, technically. We'll anyway try and see if we can get the processor to show us that, but we'll see that. Okay, so in this particular startup code, what's actually happening is, first thing I do is I check the current privilege level or exception level that the processor is running at, and I say if it's at EL2, then I have a bunch of conditional branches over here: branch greater than, branch equal, branch less than. So these 3 is for this branch, 2 is for this branch, 1 is for this branch. So this is basically assembly. All right. I'm sort of walking through this because it should make sense so that you don't get lost. So I basically check the exception level. Then based on which exception level I am, I run through a little more assembly instructions. These are all setup instructions. You might be wondering, where did I get this from? I basically looked at an existing project called U-Boot. U-Boot is like the de facto standard in this world. So there's no point sort of, writing your own assembly code. Pretty much all of this is done for you. You can just take it from there. Of course, not all of it is from there. Depending on what I needed, I've taken pieces. All right. Let me just check the chat. Any questions so far? Okay. Right. There is a question. Oh wait, no, sorry, that's not a question. Okay, good. All right. So we're now executing our assembly code. We go through all of this, and then there's this thing called BSS initialization. So I think this is a good point to actually, this is a good segue into understanding the linker script, because we've sort of looked at, these are your first instructions, you'll execute them. This is essentially where your program starts. Let's also look at a linker script. Now, if you see over here in the bootloader section, for this particular bootloader, you'll see that there's a file called link.lds. This is very similar to your memory.x file. In the Cortex-M world, the memory.x file is actually just one portion of your linker script. Okay, you're not writing the entire thing because the community has done a great job of sort of making it very easy for you to work with Cortex-M and Rust. Over here, since we're starting out, you can pretty much put your own linker script right out of the box. Okay, so you'll be writing the whole thing, not just the memory section. Okay, so here this is a very good place to actually look at what you're doing, like to give you a mental picture. So in the linker script, I'm telling the linker that I define a couple of, you can think of these as variables: page size, the stack size, the entry point, and then I say these are directives. So anytime you see these, function like specifiers over here, output format, output arch, or entry arch, these are nothing but, they're like directives. Basically, it's additional information that you give the compiler when it's going to go ahead, and the linker when they're going to compile and link the code or your program. So we're basically saying that the output format is, I'd like it to be in ELF, which is executable linkable format, and it's for a 64-bit executable. And the architecture is the 64-bit ARM architecture, which is ARch, ARM architecture 64. That's what ARch is. And then the entry point is basically this. And I'll tell you why I've sort of chosen that. It's not by accident, or it's not just randomly. That's basically, you look at the memory map and you figure out this address. And then there's these are called program headers. These are not really important right now, but I'll just sort of leave them here. Here's the other part where we see, usually you would have seen this in the Cortex-M world. You say that, okay, I go ahead and, sort of explicitly declare that this is my RAM and this is my flash and this is where it starts and this is the size of it. I do that. Same thing. I do it over here as well. In my case, Rust boot is not running on main system memory. It's actually running on what is called internal RAM, which is called on-chip RAM in the NXP world. It sort of looks something like this. Let me see if I can pull it up. So yeah, no, not this. Okay, is this visible clearly? Because it's a PDF, I just want to check. Yeah. I presume it should be. Right, I guess it's visible. So let's just sort of move forward. So this is pretty much the memory map. So the ROM code that I was talking about, where this is the piece of memory that is immutable. Neither you have access to it, neither even does the vendor have access to it. Once it's written to, it's technically supposed to be immutable. So the very first, slice of the memory map is what the ROM code takes up. Here, there's a lot of stuff that's already present. And then there's also this particular memory map that you see here, which is right here. So this out of this on-chip RAM, there's a little bit of it that's reserved for the ROM code when it runs. And then the remaining is free to use. That's what we will be using. And if you can see over here, it starts at this particular value, right? It starts at about hex 9140s, right? So I did the math and I was like, let me not start right at 9100. Let me start at, about 4 kilobytes into that because I want it to be aligned to page size and all. Okay, so I say that that's where I'd like you to, lay out, basically start laying out my program from that particular address. And then here you see a bunch of sections. Sections are what organize your code and it determines your layout. So everything that is marked as text goes into the text section. So I'm basically saying, if you see, my sections are .text. In .text, I'd like you to put all of the, from all of the compiled artifacts, all of the text sections that are present in those compiled artifacts, I want you to include them. All right. First, I basically say align it correctly to a memory address. So alignment becomes very important when you're actually dealing with this because of various reasons. I won't get into it, but just know that it's important. Here, we basically take all the text sections from all of the different compiled modules and artifacts, etc. And then we basically stick it in here. And then we're basically saying that should be present on the on-chip RAM first. That's the first thing that needs to go into the on-chip RAM memory, starting at this entry point. Okay. And then I say read-only data. This is again data that's only read-only. So you basically store some constants or some values that you don't want, to keep allocating and stuff. You put it in read-only data. Again, you add that to OC RAM. Then there's something called a global offset table for global variables that you have. You want them to also be preserved, same thing. And then lastly, there's also this data and BSS section, which is what I was talking about when we were looking at the startup code. The data in the BSS section is primarily something that needs to be, this is where you put all of your, basically all of your data that, if you're not doing heap allocations and if you want them to be allocated in BSS memory, then you could put them here. All right. This is another section for data specifically, not for instructions. So instructions only go into the text section, technically. Of course, there's a lot of different things that can happen. If you are trying to, you're trying to be an attacker or hacker, lots of things can go on. But anyway, the idea is that you're breaking down your code layout into these sections, and you're saying exactly which one should come after which one. And you're also trying to be a little more precise about the addresses where something should start, what alignments they should have, all of that. Okay. Lastly, you see that here is where I describe my stack. I say my stack needs to start after all of this is done, after you've sort of made some space for all of these things. Now you go ahead and, add a stack. And look at this, the stack over here, I'm trying to say that the stack endpoint, because the stack grows downwards, not upwards. So the stack grows downwards. In order for the stack to grow downwards, we basically assign a higher value, which is why this stack size is 8. So I take, let me just come down. I come to 8 plus 8 times 1024 is 8 kilobytes. So I am allocating a stack of at least 8 kilobytes for this particular program. Yeah. And that also is being allocated on the on-chip RAM. Okay. Does the linker script make, more sense now? You may have assumed that the linker script is just something that we just put in there. That's just a one-liner. But the linker script is actually, if you actually look at it, it's much larger. You don't get to see that in Cortex-M because what you write is just a part of the larger linker script. But if you were to look at a full linker script, this is what it looks like. Yeah, any questions in this? Okay, I guess not. Let's go to the next part. Let's go back to the assembly code. So entry.s is where you have your, we were talking about the BSS section. So that area of memory that I have allocated on the on-chip RAM for BSS, I would basically, before I start execution, I need to go ahead and zero it out, because that's going to be used by my program for whatever it needs BSS for. Okay, so that's what's happening over here. And then finally, you saw that in the linker script, you see the stack end over here. You see stack end. This stack end comes from the linker script. So if you go to the bottom, you will see that after you allocate everything, whatever is the final address, I want you to assign that address to stack end. That's what the linker is doing. It's figuring out all of this stuff after you've compiled, your code, right? This is the linking part. Same thing goes. So once that stack end is also assigned, we simply go ahead and jump to this particular symbol. You can call it label, which is start rust. Now, what is start rust? If you were to go into boot RS, you will see that start rust is an actual Rust function, and it doesn't do much over here. Its job is to basically call kernel init. That's all it needs to do. The way you do this is you simply go ahead and call global ASM. You include that assembly file that you wrote by hand. You include that in your Rust, code as a via macro called global ASM. So it's basically going to add that assembly file inline into this, into your code. And then from there, you can call start Rust. The moment you call start Rust, you're now in Rust world. Right? That makes sense, right? So pretty much that's what we were looking for the last time. But the last time we were running into things like some debug issues, some power off issues, and some things were not working properly. Now I think we can sort of get this piece working, wherein you write your little piece of assembly that takes care of a bunch of different things, set your zero out your BSS and ensure that your exception levels are correctly checked. All of that is done, and then you jump into start Rust, right? So once this is done, now you're actually in the start world. Now you can, if you go to kernel init, you will see that I'm basically initializing my what is called exception handling. I'll spend a few minutes over there. And then we load the drivers that I've written. I've written a driver for the UART. So the basic thing that you need to do, the first thing that you need to do is you need to bring up the UART, right? The UART is like the most important thing that you need when you're working with any system. Otherwise, you'll pretty much have to live your life in this particular world, which is using JTAG debugging, hardware debugging, as well as GDB, etc., which is not pretty the further you go. So the point I forgot to mention is you use this only when you don't need, or when the other ones are not sufficient to debug a problem. So this is like, this kind of debugging is very, very invasive, very, very hands-on. All right, you'll need special hardware, you'll need a special piece of software, you'll need some architectural knowledge and all of that. So the first goal should always be, once you're done with this, to get yourself a UART, basically UART working, so that you can start printing stuff, and that makes it a lot easier to get your implementations going. All right. So, and kernel initialization does nothing else. It initializes exception handling. Exception handling, I'll just come to that, and then it loads, or rather initializes the drivers that you may have written and loads them in, and then you can jump to kernel main. This is where you do all your safe stuff. So far, everything that I've just written is all unsafe. Okay, that's why you explicitly marked it as unsafe, because a lot of this stuff is, you're touching a lot of the hardware stuff, so you don't want that to be, you can't really call that safe, unless, of course, you can call it safe if you implemented it properly, but for the user to know that this part is unsafe, you clearly mention that, right? Because you're dealing with hardware, you're basically mutating hardware, which is by definition, you don't know what can happen, right? Then you move into the safe fragment of Rust, which is where kernel main sits, and then you start, using the thing that I've put over here is I've put in a bunch of print statements so that I can get some output. Now, I still don't have the UART working as far as I know, but I believe, I have all the pieces. Maybe in another stream we can get this piece also included. Okay, so far so good. Any questions on this part? Yep. Okay, guess not. Right, so now let's look at, let's get to the next step. I've just so far talked to you about, how we've just initialized all of this and made all of this work, etc. Now let's actually look at this hands-on, because that's the point of this. This is a live stream. We wanted to actually get some hands-on work on this. So if I was to sort of do this, basically spend quite a bit of time trying to get it to work. So the biggest problem that I had was GDB wouldn't work the way I wanted it to work on my machine, because I needed to patch it. And this is not a patch that's, sort sort of merged into OpenOCD's mainline tree, etc. No, this is a privately applied patch because I need to do something to specifically make this work. I'll show you what I mean by that. So in order to do that, let me just pull up my virtual machine. So I needed to pull up a virtual machine so that I can actually run this and show you what's going on. Is the font size okay over here, or do you want me to make this bigger? Can everybody see the virtual machine? Basically this window that I'm looking at, it should have like a terminal on it. I could make it a little bigger. Hope that's good. Yeah, so I presume that should be decent, right? Yes. And let me quickly add my board and my debugger, sort of turn them on, power them up. Okay, good. So people can see it. So since I've already run them and actually got this working, let me show you how this works. So the first thing is I've got my board connected. My laptop is connected to the debug probe. In this case, I'm using an FTDI chip, which is my debug probe, and that is connected via JTAG to the board. So which we all, we saw that in the last session. I'm basically going to use the same setup, and since I need root permissions, okay. Looks like I'll just need to plug it back in. Give me a minute. Okay, just a minute. Okay, that should work now. Yep. Why is it not working? Oh, sorry. Okay, looks like I'll just need to restart my machine. Well, things you do to get things to work. Wait. Right, by the way, the virtual machine is visible, right? Okay, I just wanted to double check. While I pull this up. Don't tell me you crashed. Great. Okay, just bear with me for a second. this. Okay. Yeah. So this should take a while to just, I think it should take about 30 seconds. So I presume this is sort of visible, right? Can one of you just confirm that this is visible to you guys? All right, this looks good. Let me increase the font size. Okay. So hopefully that should work. That's interesting. It was working till about now. No clues now why it's not working. So just give me 1 minute. I think my mic is the problem. Just see, let me just disconnect the mic. Don't worry, I'll just put it back up again. Okay. You guys can hear me now? Not entirely sure what's going wrong over here. Why does it keep saying no device found? Okay, I'll give it one last try. If it doesn't work, we'll just switch to the code itself. I have some debug logs anyway, which I'll try and show you if that makes sense. LS USB, yeah, that's a good point. Let me try and check that. So, we've got root hub, we've got Kivu USB drive, hard drive is there. Oh wait, let me restart the machine again because I think I know what's going on. So Yep. It's kind of why I think we should just record it when it's working so that you don't have to deal with this. But anyway, a lesson for next time. Okay. Generally, I should get a prompt when I plug in my USB drive. For some reason, I'm not getting the option. Okay. I have no clue why it suddenly decided to do this. This is definitely working. Double check this. Okay, it's definitely working. But yeah, I guess we're just going to be, have to spend a bit of time debugging this. So let's move on to the next piece, which is I wanted to talk about exception handling and timers. I believe we have like 5 minutes. We'll sort of spend some time on that. All right. So if you look at what we were doing over here, the first step was we were initializing our exception handling set. So you saw that we actually transferred control from the startup code. From our startup code, we jumped into Rust. Now that we have jumped into Rust, we need to like handle this. We need to like, because we are sort of blindly going ahead and running some instructions, we don't know. Let's say if we run into an exception, what could go wrong, right? In the ARM world, exception handling is defined pretty well. There are pretty much 4 different kinds of what you would say exceptions that are possible, but they are actually categorized into 2 different types of exceptions. One is a synchronous type of exception, the other one is asynchronous. The synchronous type of exceptions are the easy ones to understand, where you would let me actually get into this. So you would normally have like a in the synchronous type of exceptions, what you would normally have is you normally have like a you try to divide by 0, right? There is some instruction in your program, that is the code that you've written, that actually threw an exception saying, okay, this is an invalid operation, this cannot be done, right? That's a synchronous exception. Then there's asynchronous stuff. Asynchronous stuff is something like the hardware firing in timer, or you try to access some address and that was a faulty address, right? All of this stuff that you actually see that is not in response to some code that is being executed by you, that's your own code, but something external that actually happened, which is asynchronous, that's an asynchronous exception. And ARM has like 4 different types. You've got the debug, you've got the system errors, you've got the interrupts, and you've got the fast interrupts. These 3, which is system error, interrupts, and fast interrupts, are pretty much the same. They're interrupts, but with specializations, I guess. All right. But in any case, the simplest way to understand exceptions is the way we've written it over here. What we do is when you hit an exception, right? So, sorry, when you hit an exception, what happens is you pretty much go into, there's a particular register that exists. It's called the vector base address register, which is what you were seeing over here. So the handling init method is nothing but initialize exception handling. That's what it does. The goal of this is basically to set this register. It's called the vector base address register. What does the vector base address register do? It holds the address where your exception handlers are sitting. All right. So all the exception handlers that I need are actually described right here. They are all this. These are all my exception handlers. All of this. All of this is my exception handler. I have basically, I'm not doing much. What I do over here is I basically, whenever I get an exception, I print out a lot of different things and I stop. That's all I do. That's all this stuff at the bottom that you see. This is display, then display for this. All of this is just printing out the exceptions that you might have reached, that you have encountered, and then you just, stop execution. That's what we're doing over here. And in order to do that, you first set this register. It's going to hold that address, and that address is going to point to the very first exception that we are defining over here, which is, we're calling it current EL0 synchronous. So if you actually were to look at how this works, you'll see that in the assembly code that we've written, we see that the first exception that you see, which is current EL0, is over here. And I've defined that in the main Rust code, but its assembly instruction, there's an assembly counterpart to it as well. The reason is because whenever you're doing things, as I said, whenever you're doing really low level things, you generally tend to reach for assembly because it's much more straightforward and it's very direct. You're basically writing instructions, right? So it's much more direct. So in the vector base address register, I store this particular pointer to this, think about this as the first address that I'm storing the pointer to. And every other subsequent exception handler is about hex 80 bytes or 128 bytes, all right? Within that, I need to go ahead and handle the exception. Of course, you can always branch out of it if you want to do more exception handling, but you only get 128 bytes for each exception handler. There are 16 exception handlers in the ARMv8-A architecture. Okay, makes sense? So whenever you hit an exception, you look up the vector base address register, you come here, depending on which exception it is, you go ahead and pick that exception, and then you say, okay, call the exception handler, which is this. So these are the exception handlers that we've specifically defined. Make sense so far? Right? It shouldn't be it shouldn't be too complicated. It's very simple. You hit an exception, there's a specific place, you get the vector table base address register, you go there and you say, okay, I'm at this level. So if I'm at the level 0, then I'll pretty much choose only these three. Out of these three, I'll be choosing one. If I'm at any other level, then I'll choose this. Then the other ones are, slightly different, but that's how this whole thing works. Right? Any questions in this? Yeah. So any questions? All right, cool. Yeah, and I guess we are on time. So I just will cover one more piece because we didn't get to do the demo. I was actually going to show you that this thing actually works. But anyway, I think I can capture a separate recording maybe and put it in there. That should be easier. But anyway, The second piece was, you also need a timer. Why do I need a timer? Because I was going to be doing some printing and stuff. And in order to do the printing, I also want to know when I print, one log line, the sequence of logs that I print, I want to attach a timestamp to them, right? So in order to do that, I said I needed a timer. The ARM architecture provides, system timers that you can use. When I say a timer, think of a timer as some counter that is highly precise and that you can use for, any timing related work. In our case, we actually have a timer that's implemented. So the timer is a generic timer. It's basically this, okay? This is nothing but a 64-bit counter that is made available in the ARM architecture itself. It's not implementation defined. That means it's not the vendor that's adding this timer. It's part of the ARM architecture itself. All right. This is not a lot of information. This is pretty straightforward. You take the counter, you start it, and whenever you come across a point, you say, okay, I'm going to stop it here, or rather, I'm going to take another reading of that counter, and I say, okay, what is the difference? Okay, the difference is going to tell me how much time has passed. Okay, by the way, this is a counter. That's why this is not absolute time that you get. You don't get absolute time over here. All right, you only get relative time depending on a starting point. That starting point is usually the start of your program execution. All right, any questions so far? While while there are questions being asked, let me see if I can now sort of try this. Ah, crap. I don't know why this is not working. Okay, maybe. Guess not. Something is, I don't know if because I've added too many USBs or what is going wrong, but yeah, there's something wrong. I need to fix it before I can show you this. Anyway, not to worry. I'll somehow find a way to add this in as a recording so that it's available. Okay. All right. So far, I think we've covered all the pieces that we wanted to talk about, which is how do you get Rust running on the ARMv8-A architecture, number one. Number two, what is this exception handling piece? How can we use it especially when we're working with startup code? The last one is the timers piece. How does this work? Like, you can use timers in the ARM. It's not very different from Cortex-M. You've done this before. This is Cortex-VA. You're just using a timer to do a couple of things. Okay. Any questions before we wrap? No questions? So I guess we can close. Yep. Guess so. All right, guys, that's it. Have a good day. Have a good weekend, actually. Bye.